Let's now uh, learn. It's now time to learn about how to determine the potential due to continuous charge distributions. We have done something like this. We started with the electric field. We um, we did one for discrete charge distributions, and then we had continuous ones. For the discrete charge distributions, they're essentially point particles, and we add them. Since electric fields are vectors, so we apply vector addition methods for it. And for continuous charge distributions, we had a demonstration in class of how to derive them using integral forms. So these ones should be familiar to us, but there's some important differences in the integral form for the case of the potential due to continuous charge distributions. Now the thing here is we have done the discrete distributions, so it's actually a simple addition. We don't have to consider the direction or something because potential is a scalar quantity. It's the same thing with the continuous charge distributions, getting their potential. We'll do the integration. We actually just have mostly a few terms. Certainly one. We don't need to. Uh, we won't have some sort of an answer that will be having x and y's here. Now, for the form of the integral, it's uh, v equals 1 over 4 pi epsilon naught dq over r. So, well, the only major one another difference would be the denominator. Electric field integral we had r squared. For the potential is just r. So let's apply it to this example. So this is the same example as we had for the electric field. So it's the first example. So we are given the same setup. So we make a drawing here. So this is along y-axis and this is along x-axis. So we get this portion of the charge, and then we select a certain point on the x-axis and find the electric potential at that point, a distance x from the origin. So it's x, and then let's call this y. So certainly we could have x squared plus y squared square root. So it's actually that simple. Next is we define dq. So we have dq, small q rather. So dq is equal to q, and the length here is from negative a to a. So we have both the r and the dq here at this point. So let's assemble the integral. So we have b is equal to 1 over 4 pi epsilon naught. And then we have sorry, q over 2a over 1 over square root of uh, it's x squared plus y squared. And then we're gonna have to add check that. Okay, so we're gonna have to add dy here, and we get dy. So we see this form, we sort it out. Q over 2a, so they'll go outside because they're constants. And then we have dy over x squared plus y squared. Um, Let's see if we see something similar to this one. This one, the first equation looks similar. So let's try to have this form ln x. This one. So we take note here, the y variable is the x here. It's the variable of integration. So let's copy that. Q over 2a ln or x plus x squared plus a. Okay. Y plus y squared plus x squared. So the bounds here would be from negative a to a. So we have negative a to positive a. Ln y. Okay, we substitute them. Then ln a plus x squared plus a squared divided by negative a plus x squared plus a squared. So this is our answer. So this is the potential due to the line of charge bounded from negative a to a, and that's potential along x-axis. This is actually quite shorter, but we already know how to pull it off. You could do the same thing. We had an example in class for the ring of charge, then for disk. So we have ring of charge, disk of charge. You certainly have your notes there. The only difference you need to change would be the denominator here, and you could apply the integral rules here, and you could certainly figure out the potential